The topic is hashing technique. In this video, I'll be discussing about why we need hashing, what is the use of hashing, and what is the ideal hash function, the base idea about hashing. Then we'll see what are the drawbacks of ideal hash function. Then we will see modulus hash function, then its drawback, and what are the possible solutions. So let us start why we need hashing. Now let us understand why we need hashing. See, hashing is useful for searching. So if you have the list of keys and you want to search some key from them, then you can use hashing. So for searching, we already have some known search procedures. Yes, those are linear search and binary search, which we have already learned. And we already analyzed them, and we know that the time taken for linear search is order of n, and the time taken for binary search is log n. So log n is faster than n. So we know faster searching method, that is binary search. So we want still faster than this one. So what is the time that is more smaller than this one? That is 1 constant or any value that is less than log n. So we want a search method that is less than log n. So yes, for that, idea of hashing technique is introduced. So hashing will try to search the keys less than log n time. So almost constant time. So let us compare these. First we will, so let us compare these linear search and binary search and then hashing. So for explanation, I have taken set of keys here, and these keys are stored in an array as it is in the same order they are kept. Now, if the keys are as it is kept in an array which are not sorted, they are not in any order, then upon this we can perform linear search. So for performing linear search, we don't want keys in a particular order. The next one is same keys, I have kept them in the sorted order. If they are in sorted order, then we can perform binary search. So the requirement for binary search is the keys must be sorted. So this is the extra work that you have to do. If you want to apply binary search, then make sure keys are in sorted order. So for keeping them in sorted order, you have to put some extra efforts definitely. So binary search time, that is log n, can be achieved if you are putting efforts in keeping the list in sorted order. Now the third idea, that is hashing. So if we have the keys, then how they should be arranged so that we can find them in constant time. So here already I have taken an array to show you how these keys should be stored. Let us store these keys here. 8 should be stored at index 8. Then 3 should be stored at index 3. 6 at index 6. Likewise 10, 15, 18 and 4. So key is stored in the same index. Rest of the indices are empty, they are blank, they don't have any keys. So you can put there 0 or -1 to show that keys are not there. So key itself is made as an index and it is stored there. So now if I want to search for any key, let us say I want to search for 10, go to index 10, yes, 10 is there. How much time it takes to find out 10? Just constant time. I want to find out 18 is there or not. Go to index 18. So I don't have to check rest of the keys. Directly go to index 18. It's there. Yes, there. So key is found. Now suppose I want to find out a key 7. See, 7 is not there. So okay, go to index 7. Yes, it's not there. So directly go to that particular index and find out key is there or not there. It's taking just constant time. Yes, this is fastest method of searching. Yes, hashing is fastest searching method. Now drawback. The drawback of hashing is, see, I have only 7 keys available here. But what is the size of an array? Size of the array is 19. I must take 19. I have taken 20 till 0 to 19 I have taken. So I must have space 19 for this one. Because the largest number is 18, then I must have an array up to index 18. Right? So if suppose the next number, if I want to insert in this list of keys 100, then I should have an index 100 also in an array. So though I have only 8 elements, then I may be having 100 spaces. So a lot of space is required and lot of space is wasted. So this is the drawback. So we have to do something to reduce this huge consumption of space. So for that, let us start studying about hashing. So for studying about hashing, we'll represent this hashing in some mathematical model. So that mathematical model we will look at now. Yeah, let us look at mathematical model for hashing. These are the set of keys. Those set of keys, let us assume them as key space. And this is hash table, the array where we will be storing the elements or the keys. This is hash table. Keys should be mapped on hash table. So it is just like domain and range. So the elements from domain are mapped on the elements in range. So this is like a relationship. So mapping domain upon a range is a relation or a function. So let me show you what are the types of mappings available in the relations. So there are 4 relational mappings. Let us look at them. Yeah, here are 4 relational mappings. Out of these 4 mappings, one-to-one and many-to-one, these are called as functions. These are called as functions. So yes, function is a type of relation. So here we will use a function for mapping. First of all, let us map them upon based on the idea that I have given you. So let us map these. 8 should go at index 8. Okay, it is here. Then 3 should go on index 3. Then 6 should go on index 6. 10 should go on index 10. 15 on index 15. Then 9 on index 9. 4 on index 4. See, this is one-to-one mapping. Yes, every key is mapped on one index in a hash table. It is one-to-one mapping, this mapping. So it is called as function. So what is the function used here? See, the function h of x, if I give, means x is 8. Then what is the answer here? 8. If I give 10, h of 10, answer is what? 10. So h of x is equals to x. This is the function used here for mapping keys on a hash table. So we say that we are not storing the elements directly. We are using hash function. That hash function is giving us the index and we are storing a key at that index given by hash function. Yes, this is the idea. So next time when we want to search for any key, whom you should ask for index? Again hash function. Suppose I want to search for 9. H of 9, answer is what? 9. Go to index 9. See, hash function has given us the index or location where that key is present. I want to search for 12. H of 12, answer is 12. H of 12 is 12, right? Go to 12. It's not there. Key is not there. So using hash function, we will map the keys on a hash table so that for searching also use same hash function for finding an element. So when we say function, function supports 2 types of mapping, that is one-to-one or many-to-one. So our function that we are using here is one-to-one function. So this function h of x is equals to x, we call it as ideal hashing, because the time taken for searching or storing or deleting an element is constant. Just use the hash function and go and store the value there, and use the hash function and retrieve the value, so the time is constant. The time is equal to the time spent by hash function. So this is ideal hashing. Now let us talk about a drawback of ideal hashing. The drawback of ideal hashing is the space required is very huge. Lot of space is required. Even though I have only 7 elements here, then the array space I have is 0 to 16. And if I have one larger key here, like suppose I have 100, then I should have an index with 100 also. Then only it's possible to achieve ideal hashing. This is the drawback. So who is responsible for this drawback? Hash function. Who is giving the index? Hash function is giving the index. So hash function is responsible, ideal hash function. If I want to reduce the space, I want to achieve same thing hashing in limited space, then do what? Modify hash function. Modify this one. Now let us see how we can modify hash function. How much space I want to provide? I want to provide only 10 spaces, that is 0 to 9. So if I am providing only 0 to 9 spaces, then hash function should be changed. Otherwise, for 15 it will give the index 15, 15 is not there. Now let us modify hash function. So I am modifying hash function. H of x equal to x mod 10. So I will remove this space. I will take only 0 to 9 indices. Now the hash table size is 0 to 9. I am ready to provide only the size of 10 only because I have 7 keys. So I think 10 is sufficient. So I have taken space 10. So what should be the hash function? Hash function is modified that x mod 10. So this hash function will never give you value greater than 9. So you get the values from 0 to 9 only because it is mod 10. Now let us map these values once again using that hash function. So let us start. 8 mod 10. See, 8 mod 10. Mod means remainder, right? Remainder. When 8 is divided by 10, remainder is what? 8 only. Because 8 divided by 10. So it doesn't get divided 0 times. So 0 only. So remainder is what? 10. So it is 8 only. So this 8 is mapped on index 8. Then 3 mod 10. 3 only. So it's mapped there only. 6 mod 10. 6 only. Then the 10 mod 10. 10 mod 10. If this is 10, 10 once 10 and remainder is 0. So we get the index 0. So 10 should be stored here. So this modulus function has given the index 0. So I have stored there. Now 15 mod 10. So if it is 15 mod 10, 10 once 10 and then subtract this, remainder is 5. So remainder we got 5. So 15 should be stored at index 5. So that's how all the keys are stored or mapped using this hash function. Now let us see the problem with this modulus hash function, the drawback of modulus hash function. If I have a key value 25, where it should be mapped? 25 mod 10. So 10 will divide 25. So 10 to is 20. Remainder is 5. So this 25 is also mapped on index 5. This location only. See, 15 is already present there. Then 25. There is no space for 25. So two keys are mapped at same index because we have modified hash function and this modulus hash function. When two keys are mapped at same location, we call it as collision. So there is a collision of keys. And if you observe one thing, two keys mapped at same place, many to one. So this function is not 1 to 1. So this function is many to 1. So more than one keys may be mapping at the same place. Yes. 15 will be mapped there. 5 will also map there. 25 also, 35, 45. Any number ending with a 5, digit 5 will be mapped there only. So if you have multiple keys, all will be mapped there only. So this is collision. So this is the drawback of modulus function. When you modify hash function from ideal to any other function, then there is a problem of collision because ideal hash function is 1 to 1 and any other hash function if you write, if it is not 1 to 1, then definitely it is many to 1. So many to 1 means more than one keys will come on same index and that is collision. Now how to resolve this collision? So I'll show you what are the solutions for resolving this collision. So next we will see what should be done for avoiding collision. Now let us see what are the methods for resolving collision. So if a function is many to 1 and if there is a collision, 2 or more keys are mapped at same place, then how to solve that problem? So for solving the problem, there are two major methods, open hashing, closed hashing. First I'll tell you this difference. So first I will say what is closed hashing. See, the size of the hash table is a 10 and this is the space given. So we will utilize only that much space only. We will not increase the space. That is closed hashing. Then what is open hashing? We will consume extra space. Beyond this hash table, we will take more space. So that's why that is open hashing. And in that open hashing, method is chaining. We will look at these methods. So one of the method is chaining. Then in closed hashing, three methods are there. So these are under open addressing. So I'll explain what does it mean by open addressing. If two or more keys are mapped at same place, if there is collision, like suppose 25, I got the same index, but this place is already occupied. Hash function has given this place, but it is occupied. So we'll store it at any other free space. So we'll not strictly store at a place where hash function has given the address. We may store it at any other address. So that's how this is open addressing. But the question is, where will you store? There are three options: linear probing, quadratic probing, and double hashing. So we'll look at all these methods in next videos. So that's all about introduction to hashing and ideal hash function. Yeah, the topic is chaining. In the previous video, we have seen modulus hash function and the drawback of modulus hash function. That is, more than one keys will map on the same location and it causes collision. So let us see how to avoid collision or how to resolve collision. So for resolving collision, chaining is one of the method, and it is also comes under open hashing. So let us learn about this topic. So in this topic, I will be showing you how to perform following operations, like how to insert and how to search and the analysis of search. Then also we will see how to delete. So these are the operations we will learn on chaining. So let us start. I already have a set of keys kept here, and those set of keys I have taken in a key space, and the hash table size is 10. So hash function is h of x is x mod, size is 10. So I will directly write 10 here. That is the size. Now using this hash function, I will insert these keys in the hash table. So let us do it one by one. 16 mod 10 is a 6. So it is inserted at this place. Now as this is chaining, so it is not directly inserted at this place, but here a node is created, that is a linked list, and there the value is inserted. Yes. So it means this is a pointer to a linked list. Yes, this is a head pointer to a linked list. So this is a array of pointers to linked list. Yes, it is implemented using array of pointers. Then let us insert rest of them. 12 mod 10 is 2, so it is inserted at this place in a node. 25 is 5. 39, 6. This is a collision, but here we are inserting in a linked list. So I will create a new node and insert here. But 6 is smaller than 16, so 16 should go there and 6 should be inserted here. Means these keys must be inserted in the sorted order. They must be kept in sorted order so that while searching it is easy for search. 122 is greater than 12, so it's inserted there. The next is 5. 5 is mapped here. So 5 is smaller than 25. So 25, 5 comes as a node before 25. Before 25. 68, it's inserted here. 75, again mapped at 5. So 75 is greater than 5, greater than 25, so it should come here as a last node. So that's all. I have inserted all these keys, and the keys are inserted in chains. So yes, these are array of chains. So hash table is made out of array of linked lists or array of chains. See, the hash table size is 10. So beyond this, we are taking more extra space. So this linked list can go to up to any size. So you can insert as many keys as you want. There is no limit for the size here. Now we have seen insertion. Insertion was very easy. Then next, let us see how to search. I want to search for a key 12. Use hash function. 12 mod 10 is 2. Go to index 2 and search in this linked list, in this chain. So yes, 12 is found in just one comparison. Successful, search is successful. I want to search for a key 75. Take this hash function will give the index of 5, go to index 5 and search for 75 in this chain, in this linked list. Is it 75? No. Is it 75? No. Is it 75? Yes, found. So search is successful. Now search for a key 65. Take this hash function, 65 mod 10 is 5, go to index 5, search for it. 5, no, 65 is greater. 25, no, 65 is greater. 75, no, 65 is smaller. So key is not found. Key is not found. So search is unsuccessful. For these two keys it was successful. Now let him take one more key, 15. 15 mod 10, 5. Search here. Is it 15? No. 15 is greater. Is it 15? No. 15 is smaller. Stop. Don't check further. If they are sorted, that is the benefit. You can stop if the key is not found and if you got an element greater than the key that you are searching. So for 15 also search is unsuccessful. That's all. Insertion is also easy and searching is also easy. Now let us do analysis and find out how much time it is taking for searching in case of successful search as well as unsuccessful search. Now let us do analysis. I have the number of keys that are n. Suppose I have 100 keys. Here I have few keys, only 9 keys are there, but assume there are 100 keys, right? And the size of the hash table is 10 because the hash function is x mod 10. So the hash table size is 10. So in this chaining, though the size of the table is 10 only, but there is no upper limit. You can add as many keys as you want because they are getting inserted in chain. So I am taking size number of keys as 100. Now the very important thing, I'll take n by size, that is number of keys by size. This is represented with a lambda or alpha and it is called as loading factor. This loading factor is very important in hashing. So we find out loading factor. Loading factor is number of keys divided by size of the table. Now remember one thing. All the data structures that we have analyzed so far, we were analyzing them based on a number of elements, n. But here it is not based on number of elements, that is not based on keys, n. But it is based on loading factor. So analysis of hashing is always done based on loading factor. Remember this one. So as per our example, if I say I have 100 keys and the size is 10, hash table size is 10 means 100 by 10 is 10. So the loading factor is 10. So what does it mean? It means that at each location there are 10 keys. There are 10 locations. At each location there are 10 keys. Because this is a chaining, we got the loading factor greater than 1. We got the value 10. So with this 10, we are assuming that the 100 keys that I have are uniformly distributed at each location. So each location is having around 10 keys. We are assuming this. Our assumption may be wrong, but we are assuming this, or actually we are expecting this. We are expecting that every location is having 10 elements if I have 100 elements. So if you observe in this example what we have seen, one element and two elements, this is having 3 elements and they are not having any elements. These are still empty. These are empty, right? These are nulls still. Anyway, the reality is something else, but we are assuming that the keys are uniformly distributed. Now based on this, we will do analysis. Now let us see what is the time taken for searching in case of successful search. Time taken for successful search. So for successful search, we say time is, first of all, we use hash function for getting the index and that takes constant time, 1. Yes, 1 for computing hash function, which takes constant time. Second one is We have to search in that particular chain, in that particular linked list. So what could be the average time? Average time will be half of that loading factor. So we are assuming that at each location 10 keys are there. So for searching, maximum how many comparisons? 10 comparison. Minimum how many comparison? Just one comparison. Average how many? Half of it. So whatever the lambda is, lambda by 2. So this is the time taken in case of successful search, and this is average time. This is average time, right? Average successful search time. 1 plus lambda by 2. 1 is for hash function, lambda is the loading factor, by 2 gives average. Then what is the time in case of unsuccessful search if the key is not found? For average unsuccessful search time, for searching any key we use hash function. So for hash function time is 1. 1 plus key is not found means we may be checking entire linked list, entire chain. We don't know where it may stop. So we say that maximum time it takes. So that how many keys are there? 10 keys are there. That's what lambda. So it is 1 plus lambda. So we are taking maximum time here. The maximum possible time. We don't know when it will stop, right? So it means we assume that it will stop at the end. So the key is not found. So it is lambda. 1 plus lambda. So for searching, successful search, this is the time taken, and unsuccessful search, this is the time taken. So I have discussed searching, analysis also. Now the last thing is delete. Let us see how to delete any key. Suppose I want to delete a key 12. This key I want to delete. So for deleting 12, use hash function. It gives index 2, go to index 2, search in this chain. If it is found, delete a node. Simply it is just like deleting a node from linked list. So deleting a node. If it is found, delete it. So the procedure is simple. So for insert, search and delete, for all of them procedure is simple. Insertion time you insert in a linked list. Search time you search for it. Search in a linked list. And deletion time you delete a node from a linked list. So the operations are same as linked list. So that's all about the operations in case of chaining. Now few important things in this one. See, the hash function need not be x mod 10. We are doing it based on last digit. Last digit. That is, we are looking at last digit. If you say no, I want to look at second digit, okay, you can look at second digit also from right side, right? Second last digit. So you can write a hash function for that one also. Hash function will be h of x is equals to x divided by 10, then mod 10. If you want, you can modify the hash function. It's not necessary that you take mod means last digit only. The benefit of mod is the size of the table will be limited. So if you say mod 10, you need the size from 0 to 9 only. That is 10. If you say mod 20, then the size of the table can be from 0 to 19. So you can limit the size of a hash table. That's why we use mod. But for generating the indices, you don't have to take always last digit only. You can take any digit. Now I will show you one problem. And from that problem, after that problem, we will also see a solution. Just watch here. See, suppose I have the keys like 5, 35, 95, 145, 175, 265, 845, 55, 25. All the keys are ending with 5 only. If I use this hash function, this mod 10, then all the keys will be mapped at same index 5 and the chain of all the keys will be formed here only and all will be empty. Yes. So the idea that loading factor means the keys are uniformly distributed, that fails. That fails. That assumption fails. So then who is responsible? Hash function. Hash function. Hash function, is it a standard one that you must take this only? No, you can take any hash function. Then who is responsible? The person or a programmer who has selected the hash function. So you select the hash function such that The keys are uniformly distributed. Yes. So we assume that you have selected a proper hash function which is uniformly distributing the keys. That's why we do the analysis based on lambda. If you're not selecting a proper hash function, you don't know hashing. Simply. Don't blame hashing technique. You don't know how to use hashing. That is the meaning. Then how to decide hash function? You must have idea about the keys that you are going to insert. Yes, you must have the idea. What keys you are inserting, what is your data, you should know. Then only you will find a solution, right? Without knowing data, you cannot find a solution. So you can select a hash function such that at least to major extent the keys are uniformly distributed. So we are assuming that approximate distribution, right? So it's not accurate uniform distribution. Approximately 10 keys are there at each location, more or less, not a problem. So that's all about chaining as a resolution method or resolution technique in hashing. Now we have other methods also. We'll look at them in next videos. In this video, we will implement hashing using chaining. So I will start a new project and I will call it as chaining, and it is using C language program. Okay, create this project. For implementing chaining, we require linked list. So we have already written programs for linked list. So I will copy the required code for implementing linked list like insert and delete and search. So I'll create a new header file, and this header file I will call it as chains. Now inside this header file, I will copy the code for linked list. So here I will paste the code for linked list. There's a node structure with the data and the next pointer. And insert, this is sorted insert, because as I told you that we can insert the element in the sorted order, so that's easy for insertion searching purpose. So this is sorted insert, and then this is searching for a key element. Now the sorted insert will take a pointer to a pointer. So we will see this one now. Let us come back to the main function. So in the main function, I should have a hash table. So hash table is a structure node array of pointers. So let us take the size as 10. So I have an hash table of size 10. This hash table should be initialized. So for that, I will use a for loop and it will initialize this one. I is less than 10. I plus plus hash table of I is equal to null, is assigned with null. Now hash table is ready. Now we should have a function for inserting in a hash table. So let us write a function that is insert in a hash table. So for inserting in a hash table, it should take a parameter that is hash table. So the same thing, struct node star, and let us call it as h. It's an array of pointers and the key to be inserted. Now insert function need hash code. So for that I will write a function called hash, which takes a key, and here it returns key mod size. Size is 10. Directly I am writing size 10 this time. I have not taken a symbolic constant. Now this insert function should insert an element at given index. So I should get the index from hash function by sending a key. Now inside an array of chains that is at a given index, I should perform insert. So I will call a function that is sorted insert, and I should send the address of this location, that is address, and the key that I want to insert. That's all. This should insert an element at a given index. Sorted index function is already there in a linked list. Now here inside the main function, I will perform insert. I will send hash table, comma, key is 12. Then I will insert one more element with the same index. So let us see whether it will insert in that same chain or not. Insert hash table and the value is 42. Now I'll put a breakpoint here and then run it. Yes, it has executed. Let us check hash table. This is second index. Yes, it is having value 12. The next the value is 22 and the next the value is okay. Two values are inserted. Okay, 42 is not yet inserted because I have stopped at 42. If I continue execution, then 42 will also be inserted. 12, 22 and 42, if you look into this debug area, you can find it. So this is about insert. Now let us perform search also and confirm it. I'll call a function search. So for that, I need a temporary pointer for a node because it returns a node structure. Struct node star. I'll take a variable like pointer temp. So temp assign call function search by passing hash table of hash function of key. Whatever the value written by that hash function, we will send it that index and also the key. So now here I will print percentile D and the value is temp caps data. So here key value that I will give it as 22. Let us run and see. Yeah, this is also 22. This is an error. So I'll send the hash table index of 22 and the key that I want to search in that particular place. Yes, it is found. If I give any other key like say 21 which is not present, then I should get an error here because I am trying to access its data where there is no such node. So I should get an error. Yes, I got a runtime error because 21 is not present, so it will go to index 1 and there it is null. So null's data is giving an error. So that's it. I have implemented only insert and search. So if you want, you can implement delete also. This was just a demonstration program for hashing. Now the applications of hashing are very vast. They are used at many places to reduce the time taken for searching. So that's all in this video. The topic is linear probing. It is a collision resolution technique. In the previous video we saw chaining. Now this is linear probing. So this is another technique, that is linear probing. This comes under closed hashing. So we'll try to utilize the space given for hash table only, will not consume any extra space. So first I'll explain you what does it mean by linear probing. Then in that I will explain these operations insert, search, and we will do analysis on search. Then also we'll say delete. Now let me explain linear probing. So for explanation, already I have taken a key space, that is set of keys, and a hash table of size 10, and the hash function is h of x equal to x mod 10. But we will be using modified hash function for linear probing, that is h dash of x. That is h of x plus f of I, then result mod by 10. What is f of I? F of I is equals to I. What is I? I takes the values starting from 0, 1, 2 onwards. Now I will show you how to insert these keys. Inserting these keys procedure is very simple. Now without using that function, directly I will use this function and I explain you. Then I'll explain you how we are actually following that function. So let us start. First key is 26. 26 mod 10 is 6, so it will get stored here. So there is nothing here. It is free, empty. So 26 is stored here. So we are not forming a linked list like in chaining. This is a place for storing a key. So we have stored it. The next is 30 mod 10 gives 0. So 30 is stored here. 45 mod 10 gives index 5. So 45 is stored here. Then 23 mod 10 is a 3, so 23 is stored here. Now next, observe this. 25, this is a collision. So after inserting few keys, I got a collision here. See, 25 is mapped here only, but this place is already occupied. Then I cannot have two keys at same place. Then do what? It's linear probing, open addressing. So try to store it at a next space. Again, there is a key available there. It's not free. So okay, try to store it at next space. Yes, this is free. So 25 is stored here. See, 25 was mapped here, but there was no place here. So no place here. This was vacant, so we have used this one. So this is linear probing. So after how many collisions we got that free space? 2 collisions. So after 2 probes, we got a free space. So it's very simple. Whenever there is a collision, try to store an element at a next free space. Now let me show you how that function is used, what that function says. For 25, let us do it. H dash of 25 is H of 25 plus F of 0 mod 10. So result is 25, H of 25, this is the hash function. Result is 5 plus F of 0. F of I is I, right? F of I is I. So this is 0 only. 0 mod 10. So answer is 5. So this has given index 5. But there is a collision. We have used that function, right? So collision. Then next what we'll do? H dash of 25 we will calculate once again. H of 25 plus F of 1 this time, right? I value is taking from 0 onwards. So first 0 we tried, then next 1 mod 10. So this is 5 plus F of 1, that is F of I is I. So if 1 is 1 only, so this is 1 mod 10. So the result is 6. Check at index 6. Already key is there, it's not vacant. Then try next value of I. Then H dash of 25 is H of 25 plus F of 2 this time. F of 0, F of 1, then F of 2 mod 10. This is 5 plus this will be 2 mod 10 is 7. Yes, check at 7. There is no collision, so we store this. So this how this function is computed more than one time. First time collision, second time collision, third time we got a space. So instead of following that function step by step, just I said store it at next free space. That's what the function is saying. Now let me insert remaining keys. 43, it is mapped here. There is a collision. So we use that same function. F of I value 0, there is a collision. Then calculate with I value 1. Next place, yes, it is free. So store 43 here. The next 74 is mapped here. Already occupied. The next occupied, next, yes, this is free. So 74 will come here. See, very long distance. Actually, it was mapped at 4, but it's stored at 8. So many collisions. For storing 74, 1, 2, 3, 4 collisions. So after 4 collision, it got stored. So that's it. In this linear probing solution, there may be many collisions, right? More than one collisions are possible. And we try to probe linearly until we get a space. Now I will add 2 more keys and show you. One is 19. So 19 will be mapped here. 19 goes here. This is free. There was no collision. Now next I will insert 29. 29. Let me evaluate it here. H dash of 29 is H of 29 plus F of 0 mod 10. This is 29. H of 29 is what? 9 plus F of 0 is 0. Mod 10 is a 9 only, but there is a collision. There is a collision. Then try next value of F of I, right? Let us try that. It will be 9 plus F of 1 it will be. So 1 mod 10, that is 0. So try 0. So it's going cyclic. See, because we have given mod 10 here, 10 is the size of the table, so it will go cyclic. So try at 0, it is also occupied. Then try next one, 9 plus f of 2 you try. So 2 mod 10, that is 11 mod 10 is 1. So try at 1, yes, it is found. So 29 is stored here. So this is how insertion is done. So I have inserted 19 and 29 to show you that the places are found circularly, right? Circularly. Though we are going linear, but once we have reached the end of a table, then again we'll start from the top. So that's all about insertion. Now let us see how to search for the keys. So for searching also we use the same hash function. This function will be sufficient for us for searching. Let us look at it. Suppose I want to search for a key 45. 45 mod 10. Go to this place. Yes, key is found. Yes, search is successful. I want to search for a key 74. 74 mod 10 gives us index 4. Is it 74? No. Is it 74? No. Is it 74? No. Is it 74? No. Is it 74? Yes. Stop. We got the key. Stop. See how many comparisons we have done. 1, 2, 3, 4, 5. 5 comparisons we have done. That's it. So this linear probing method is little time taking, right? It's not constant. It's more than constant. So it's little time taking. So search is successful. 74 is found. Let us try for a key 40. 40. Now watch this. 40. 40 mod 10, 0. Is it 40? No. Is it 40? No. Next place, it's vacant. So you should stop your search once you got a free space. If you got a free space, then you should stop. So listen carefully. I know you got one doubt. That answer you will know in a short while. Now listen carefully. I know you got one doubt. You get the answer to it. Listen once again. When a key is being searched, use the hash function, go to that index. If it's not equal, next, not equal, empty place, stop. Empty place found means element is not there. So the method for searching is take a hash function, get the index, go to that index. Go on searching linearly until if the key is found or you got a free space. So this was unsuccessful. 40 was not found. So that's all. I have shown you how to search. Right? Now I'll come to analysis. Let us do analysis. I'll remove this and I'll do analysis. Now let us do analysis. Already in chaining I have explained you that analysis of hashing is done based on loading factor. It is not done based on number of elements. In all the data structures, we have done it based on the number of elements, size of the input, but it is never done based on size of input. If you try to do it on size of input, then the answer is order of n, always. So hashing will be same as linear search. So we'll do the analysis based on loading factor. So what is loading factor? Loading factor is number of elements or number of keys divided by the size of a table. So in my example, if you see the size of the table is 10 and the number of elements I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I calculate loading factor in my example, loading factor is 9 by 10. This is 0.9. So loading factor is 0.9 in our example. See, loading factor we got in decimal, that is less than 1. In the chaining it was greater than 1. But here the size of the table is fixed, so you cannot exceed the size. So that's why it is less than 1. Yes, always loading factor will be less than 1 only. It will be in decimal. Now one important thing, that is very important thing, that is loading factor should always be less than or equal to 0.5. It should not exceed 0.5. This point is very important to answer many doubts or clear many doubts. It means that if the hash table size is 10, you should not fill more than 5 keys. More than 5 keys, right? So whatever the size of the hash table, at most it can be half filled. You see in my example, I have size 10, but I have inserted 9 keys. That is wrong. That is wrong. For explanation purpose, I have taken small size and I have shown you more keys so I can show you various possibilities. But this is wrong. You should not have more than 5 keys. So that's it. If you have half of the table is empty, then a lot of free spaces will be there. Then while searching, if you remember, for unsuccessful search, we stop whenever we get free space. Then we can easily stop. We can get a lot of free spaces. So here in my example, I have only one free space because I have inserted 9 keys, which is wrong. Alright. So lambda should be less than 0.5. So lambda should be less than equal to 0.5, right? I think this has cleared many doubts. Then what is the time taken? Time is dependent on the loading factor. So average successful time, this is a known formula. So we don't have to do analysis. This is a known formula. Just you have to accept this formula. And average unsuccessful search time is 1 by 1 minus lambda. So these are the successful search and unsuccessful search average times for linear probing. Now, drawback of linear probing. First of all, you have to keep half of the hash table vacant, so space wasted. Yes. Second thing, lot of keys may be accumulating at one place and forming a cluster. They all are forming a single group, and that is cluster. Continuous you may have keys. So when you are searching for something, for example, if suppose 74 is not there and even 25 is also not there, assume that. Now I am searching for 34. If I am searching for 34. So for 34, you go to index 4. Is it 34? No. Is it 34? No. Is it 34? No. There is a free space, blank space. So we reach blank space, key is not found. So for searching some key that belongs to index 4, we are comparing with those keys also which doesn't belong to index 4. They belong to some other index. So different keys together may form a cluster, a block of keys at one place. So this is the drawback. We call it as primary clustering. So linear probing have a problem of primary clustering of keys, that is group of keys together at one place. Now let us look at delete. Suppose I want to delete 25. This key I want to delete. Use hash function, go to that particular index, that is 5. Then start searching for 25. Is it 25? No. Is it 25? No. Is it 25? Yes, found. Then delete it. 25 is removed. So I will write it outside. This place is vacant. Is it right? Is it right? What about the 74? 74 was kept here because there was no space here. 74 actually belongs to location 4. So if this is free, then 74 should be moved here. Yes, it should be moved there. So it's not simple that you just delete a key and leave the place vacant. Now imagine if I am searching for 74, what happens? 74, 4, is it 74? No, no, free space, stop, 74 is not there. So if you don't fill this space by 74, 74 cannot be searched at all. So you have to shift this key. You have to shift that key. Shifting that key, is it that easy? No. Let us see. Suppose I am deleting 45. If 45 is gone, shall I shift this 26 above this one? No, 26 belongs to this place only. There is no meaning in shifting. So shifting is not easy. You have to check whether it belongs to that index or the next index, what it is. So there are many things. So solution for this one is, if really you want to delete, then search for the key. If it is found, then take out all the keys and insert all the keys once again. So that is called as rehashing. So the solution for deletion is not simple. When you want to delete a key, you have to adjust the rest of the keys, and there are a lot of things that you have to take care. So for that, better take out all the keys and insert them once again one by one. So this is a lot of efforts, lot of work. Yes. So that is the reason in linear probing, we don't suggest deletion of element. We don't delete the elements. We don't suggest deletion. Otherwise, what we do is, If really you want to delete it, then one thing you can do is you can have some flag to show whether this key is there or not there. So parallelly along with the table, you can have a flag and show that this key is not there. So this is there, this is there, this is there. So this is not there. So I can put a flag beside each key to show it is present or not present, if at all really you want to delete, because rehashing is not suggested, it is time consuming. So I should say deletion is not easy in linear probing. So we don't recommend deletion in linear probing. So that's all about linear probing. Next video will look at quadratic probing. It is more similar to linear probing only with a minor difference. So that's all in this video. In this video, I will show you a program for hashing that is unique using linear probing. So we'll write a C language program for linear probing. I'll call the project name as hashing and the language is C language. Let us create a project. For implementing hashing, we need an array for hash table. So I'll call an array as ht of type integer and I will take an array of size just 10. I'll limit the hash table size as 10. Then as the size is 10, so on the top I will use hash define for giving the size as 10. Now for inserting or searching in this hash table, I need the function. So first function I will implement, that is insert. Insert, it should take a array as hash table. So I'll just give it as h. And next thing is key. And the size is already mentioned as a constant, symbolic constant, that is size 10. So first of all, I will write on a insert function. So for that, function name is void insert and it will take a hash table for inserting an element and also a key to be inserted. Now this function needs an index using hash function. So I will write a hash function. Hash function will take a key and returns index. So index is key mod size. So key mod size. Then this insert function should call that hash function and get the index of an element. So I will declare a variable index and call hash by passing a key. Now if that index is already occupied, then we should find the next free index. So first of all, I will check whether that index is free or not. If hash table of index is not equal to 0, it means it's already occupied. Then I need another new index where I should insert an element. So for that, I will call next function, that is probe. So it will find out next free space. So to this function, I'll send a hash table as well as the key to be inserted. So let us write one more function called probe, which will linearly check and find out a next free space, that is using linear probing. So function name is probe and it takes a hash table, array as well as key. Now again here, let it call hash function. Hash function will give the hash code for the key, that is index for the key. Now using a loop, I should find out a next free space. So for that, I will declare a variable I, which will be incrementing until a free space is found. So while inside a hash table, index plus I should perform mod once again, that is mod size. And until this is not equal to 0, I should go on incrementing I. And once a free space with value 0 is found, let us return index plus I mod size. So this is the free space for inserting an element. That's it. So this probe will return a new free index where a key value can be inserted. So at that place, we will insert an element in a hash table. So h of index assign key. So this is an insert function. Let us first try this insert function and check it. So here I will insert few keys. Insert 12. This should be inserted at index 2. I will also pass hash table ht and 12 is inserted. Then insert hash table 25. Then I'll insert one more value, that is hash table 35. Let us see where it will be inserted. And I will also insert one more value, that is hash table 26. Now here I'll put a breakpoint and I will run the program. You can watch in the debug area that no value is inserted, hash table is empty. Then if I continue debugging, now 12 is inserted at index 2 inside the debug area, you can see. Then next is 25 is inserted at index 5. The next 35, there was no free space, so it is inserted at next free space, that is 6. Now 26 should come here, but there is a collision, so 26 should be inserted at next free space. Yes, 26 is inserted at next free space. So that's it. So as the hash table size is 10, so I should not insert more than 5 values. So I'll stop here. I have already inserted 4 elements. So insert is inserting the elements. Now let us perform search or lookup. So I will call it as search. So search should give me an index. So it needs hash table, array, and a key to be inserted. Now first of all, it should get the index from hash table. So hash function, it should pass a key to get the index. Then while so as this is linear probing, it should check whether the value is present or not, the key value is present at that index or not. If not, it should perform linear probing. So using while loop, I will do that. So for that, I will take a variable I, which is initialized to 0. Now while until the key is found, we will search for it. So inside the hash table, we will take the index plus I mod size. So this is the hash function for linear probing, and as long as that is not equal to key, we will continue searching and we will be incrementing I. And once it is found, we will return index plus I mod size. This I should put it inside brackets. Yes. So this will find out an element by performing linear probing. This loop is for linear probing. I already have a function for probe, but that probe function is for insertion purpose. I am using it. Now for searching also, I should have different probe because this probe function is looking for free space, and for searching it needs to check for key value. Now let us try for search function and check. So here I will directly print the result sent by search function, and here I will say key found at so and so index. So I'll use /n and call search, and I want to search for key 35. So 35 is inserted at 26. So 35 is inserted at index 6. It should return index 6. Let us run the program. Oh, search is taking too few parameters. I should pass hash table also. Yes, key found at index 6. So that's all. This is a simple C language program for hash table, and this is for linear probing. Now I'll give you an idea here, just a hint, so that you can implement quadratic probing. So instead of just I, here you have to write I into I. So this place I into I, this will be a quadratic probing. And wherever you are using I along with index, write I into I, that is I multiplied by I. So here also you can write I into I. So this will become a quadratic probing. So that's all in this video. This is a simple implementation of hash function of size 10 by using linear probing. Now the topic is quadratic probing. This is one of the collision resolution technique and it comes under open addressing. So if there is a collision, we try to store an element at some free space in a hash table, and the hash table, whatever the space is given, we try to utilize that same space. So in the previous video we saw linear probing. In linear probing there was a problem of clustering of element or primary clustering of element. That group of elements were forming a single block. So to avoid that we have introduced quadratic probing. So let us learn about this one. So for explanation I have taken an example. Let us look at the example. I have keys in a key space. I have just taken 4 keys here and this is a hash table of size 10. I have taken keys that are less than half the size of the hash table. As I already said that loading factor should not be more than 0.5. So I have taken only 4 keys to explain. This is the hash function, modulus hash function. 10 is the size of the table, so this is 10. Then this is a modified hash function used for quadratic probing. So if you see, it looks similar only. H dash of x is h of x plus f of I mod 10. Yes, it is same. Here there is a difference. F of I is equals to I square. F of I is equals to I square. And I takes value 0, 1, 2, so on. So this is the difference between linear probing and quadratic probing. The next position is found with quadratic value, not a linear value. So it means in linear probing, if there is a collision, we were trying to insert an element at next free space, but here we will be giving a little gap. We will be storing at a little distant place. So how insertion is done? Let us look at this one. See, I have keys here. 23 mod 10, 3. So 23 is stored here only. Then 43 mod 10. This is also mapped here. So there is a collision. So for 43, I will calculate h of 43. This is h of 43 plus f of 0. So first time when it is 0, then this is 3 plus 0 mod 10. This is 3. But there is a collision. The next is 3 plus, this should be 1. So when it is 1 means this is 1 square, 1. So 1 mod 10, that is 4. So yes, there is a free space. So 43 is stored at next free space here. Now next 13 mod 10, 3 only, same place. So now this is also mapping there. Let us do it. So I will just change this one instead of writing once again 1. Now it is 0, right? So we get the index 3. There is a collision. Next time it is 1. So we get the index 4. That is again collision. Next we will do 3 plus. This will become 2. So 2 square is 4. Mod 10. That is 7. So yes, this 13 is stored at this 7. Index 7. So you can see that element is stored with a little distance if there is a collision. So it means in this 3, first time we added 0, next time we added 1, next time we added 4, next time we'll be adding 9. So square, quadratic. So that's how this is quadratic probing. Now I have one more last element, 27. This will be mapped here, but there is a collision. So first with a 0 it will be a collision. This will be 7 and plus 0 it is collision. Then 7 plus 1, 8. It is stored at 8. So 27 is stored at 8. That's all about quadratic probing. So I don't have to explain much in this one. It is same as linear probing. Only the difference is we are getting the next location with a distance apart. That is not close or consecutive locations. Then about the analysis, there is a known formula. I will write down the formula. So here are the formulas for average successful search and average unsuccessful search. Just you have to accept these formulas and use them if required. That's all about quadratic probing. Now the topic is double hashing. We have already seen linear probing and quadratic probing. Those were the methods for resolving collision. So this is also a method for resolving collision. The idea here is we will have two hash function. One is the basic hash function. Then if there is a collision, then the other hash function will help us to remove collision. So for explanation, I have taken an example here. See, this is the first hash function, x mod 10. So that is a regular hash function that we have used in various examples. So h1 is x mod 10 because the size of the hash table is 10. Then this is the second hash function. That r is a primary number that is smaller than the size of the hash table. So the size of the hash table is 10, and less than 10, what is the nearest prime number? That is 7. So r should be 7. I will modify it. So I have modified it to 7. Actually, second hash function is having two desired properties. One is it should never give a result 0. It should not give index 0, first one. And the second thing is it should try to probe all the locations. Means whenever there is a collision, it should not give the indices in the same pattern. It should give different indices such that all the locations are utilized. So for that, the suggestion is this form of hash function with a prime number. So this is the suggested hash function, so we use this one. Or else you can design any other hash function you like. But two things you have to take care. The result of that hash function should not be 0. And the second thing is it should try to cover all the indices. The next thing, we will use regular hash function. If there is a collision, then we will try to use this modified hash function. So let me explain this modified hash function. This is h1, this one, same, plus I into result of second hash function. And this entire result is mod by the size of the hash table. Then this value should be multiplied by I, where I takes the value 0, 1, 2 onwards. So it is similar to linear probing and quadratic probing. So first time when you are using, I value will be 0. So this is of no use. So we can say that directly we'll use this hash function for first time. Second time onwards, I value will be 1. Then this is considerable. Then we can use this modified hash function. So for demonstrating double hashing, I already have a key space and the hash table ready. Let us map these keys on the hash table using this double hashing. So let us start. First key is 5. 5 mod 10 is 5 only. So this is mapped on a location 5. So 5 is stored here. Then 25. 25 mod 10 is 5. So this is again mapped on the same location. So this is a collision. Then I should use this modified hash function. Modified hash function for 25 is this result we got it as 5. So 5 plus I should be 1 now. Earlier I was 0. That's why we took directly 5 and found that there is a collision. Now I should be 1 into h2 of x. So I should write down 25 here. So what is the result of 25? I will calculate it. 7 minus 25 mod 7. So this is 7 minus, this is 4. So this is 3. So it should be 3 mod 10. This will be 5 plus 3, that is 8. So 25 should be stored at index 8. So 25 is stored here. Now next 15. See, the keys I have taken all are ending with 5, so they will collide with this index, right? So all are colliding only, so we can see its extreme cases also. So let us map 15. 15 mod 10 is the same index. Collision. Now let us use this modified hash function for 15. The result of this function was 5, so that is a collision. 5 plus, now 1 into, we have to get the result of this function, that is h2 of x. X is 15, so I will evaluate this one. 7 minus 15 mod 7. 7 minus, see, 7 will divide 15 for 2 times, 14, remainder is 1. So this is 7 minus 1, this is 6. So This is 6 mod 10. So 5 plus 5 is for this one, plus as it is, I is 1, then h2 of x is 6 that I have evaluated here. So this is 11 mod 10. So the answer is 1. So this 15 should be stored at index 1. The next key is 35. 35 mod 10 is a 5. So there is a collision. It will map there only. Then we should use this modified hash function. H dash of 35 is h1 of 35. Just now we got the answer as 5. So 5 plus I should be 1 now into h2 of 35. Let us calculate 7 minus 35 mod 7. So 7 minus, this is 0. 35 will get exactly divided by 7. So remainder is 0. So this is 7 minus 0 is 7. So this is 7 mod 10. So this is 5 plus 7, that is 12. Mod 10 is 2. So 35 should be stored at 2. So one thing to observe here is that whenever there is a collision for any key, when I am finding out modified hash function value, I am getting different locations. In linear probing or quadratic probing, we were getting same location, next plus 1 or plus 4, like plus 1 and plus 1. So every time next location in linear probing. And quadratic probing was giving us plus 1 or plus 4 or plus 9. So it was quadratic. But here every time we are getting different location, though all these elements are being mapped at same index 5. So that's what this double hash function is giving us different locations for different keys. Now the last one remaining is 95. 95 mod 10. So remainder is 5 again. So it will be mapped here only. So for 95 I will calculate here. H dash of 95 is 5 plus, this is 5 plus I should be 1 into h2 of x, that is 7 minus key mod 7. 7 minus key is 95 mod 7. So what is the result here? So this is 7 and remainder if you check, this will be 4. So the answer is 3. See, when we evaluate this answer is 3. For 25 also we got the same thing. Then for 95 we are getting 3 once again. Right? So this is 5 plus 1 into 3 mod 10. This is 8. 5 plus 3, 8 mod 10 is 8. So 8. Now this is second collision. See, for this key we got 2 collisions. Till now we did not get 2 collisions at all. Every time the key was placed at some unique place, that was empty place. So just only one collision was happening. Second time we were getting a free space. But now this is collision once again. Then what I should do? I should calculate the same thing with 2 here. So that's why now I is taking value 2 now. First time 0, that was just 5. Now 1, it has given us 8. Then 2. So this will be 5 plus 6, 11. 11 mod 10 is 1. 1 is already occupied. So again collision. So total 3 collision. 1 at 5, index 5, then at 8, then at 1. So I have to modify this I and take the next value of I, that is 3. So this is 5 plus 9, that is 14 mod 10 is 4. Yes, 4 is vacant. Write down 95 here. So this is the key for which there were more than one collisions. Otherwise, just one collision, second index was valid index or empty location. So this double hashing reduces collisions. So that's all about hashing. So we have seen various hashing methods: chaining, linear probing, quadratic probing, and double hashing. So that's all about hashing methods. So then in the next video, we'll look at hash functions, various hash functions, and also we'll have some general discussion about hashing. In this video lecture, we will talk about different hashing functions. Few suggested hashing functions we will look at. The different ideas for hashing functions are modulus hash function, which we have already used it, and next is mid-square hash function and folding hash function. So I'll explain about those hash functions. See, the first and the foremost requirement or the property of hash function is the hash function should be selected such that the values in a hash table must be uniformly distributed. Whether you are using chaining or you are using open addressing, that is linear probing or quadratic probing, whatever the method is used, the values in a hash table must be uniformly distributed. All the values should not be concentrated or collided at the same place every time. So this is the first and foremost property. So this is the important property of a hash function. So selection of hash function depends on a programmer or the designer who is designing a system. So one should already have the idea about the data that you are going to insert in this one. Based on that, you can select the size of the hash table as well as the type of hash function so that the collisions are avoided. If collisions are avoided, then the values will be uniformly distributed. And the next thing, if you are using chaining, then the hash table size can be anything. But if you are using linear probing, then the hash table size should be double the number of elements that you are going to insert. Suppose you are going to insert 10 elements, then the size of the hash table must be 20. It should be double. If you are using linear probing, that you are going to insert the elements only inside the hash table. So it means the loading factor of hash table must be less than or equal to 0.5, half filled. Yes, definitely you have to give extra space for achieving hashing. Now let us talk about these hash function. So first hash function, we have already seen that we have been writing this hash function h of x equals x mod whatever the size of the hash table is. So this mod function will give the values starting from 0 onwards. Suppose you don't want the values starting from 0 onwards, then you can add +1. Sometime it is taken like this also. If suppose the array is starting from index 1 onwards, then we don't want 0, we want minimum value as 1. So after that you can add 1, so that minimum value you get as 1. So anyway, with +1 or without +1, you can define a modulus hash function. Now next important thing, what should be the size of the hash table? As I said that it should be double the number of the keys, but it is preferred that the size is a prime number so that the collisions are reduced, because prime number division, because the prime numbers will have only two factors, that is 1 and the number itself. That's the reason it is suggested the size of the hash table must be a prime number. Like here, just for an example, I have taken a hash table of size 9, but it's better if it is 11, that is prime number, or 13 or 17. So it's better we take a prime number as the size of a hash table. Then we don't have to discuss much about this one. Then the second method let us look at, that is mid-square method. So that method suggests that whatever the key is, you do square of that key and take the middle digit. For example, I take a small key, let us say it is 11, key is 11. I want to insert 11. So where it should be inserted? First of all, perform square of this 11. This gives 121. Then take middle digit 2. So this 11 should be stored at index 2. While storing we follow this, and while searching also, when the number is 11, then square it. So we get 121, then take the middle digit and go to that place. Yes, 11 is found. So I have taken a small number, that is 11. If suppose key is 13, then perform 13 square, that is 169. Then the middle digit is 6. It should go on index 6. So in my example, I have taken 2 digits number. So square of that I am getting 3 digits. Suppose the key is bigger than this one, then you may get more number of digits. Suppose you have 5 digits, then you can take this middle digit. Or if you have 6 digits, after performing square, if you are getting 6 digits, then we can take middle 2 digits also. Suppose this middle 2 digits are not there in the hash table, then you can perform mod on that one. So mod is always there. So even after taking middle of a square of a key, you can still perform mod so that you can get a position within the size of a hash table. So this is the idea of mid square, taking a square of a key, then taking middle digits. You can take 1 digit or you can take more number of digits, that's up to you. Then let us look at folding method. Suppose a key is 1, 2, 3, 3, 4, 7. I have a 6-digit key. We can partition the key into more than one partitions by taking some number of digits. So here I will take two digits. Then first 2 digits is a number 12. The next 2 digit is number 33. The next 2 digits is 47. Then add these digits 12, 9. So we got a number 92. This 92 should be an index in hash table. So folding is we are taking digits and it is just like we are folding these digits and making them as a single number. Then this number can be used as an index for hash table, and again if you think that this number is larger, then you can perform mod, or else you can add these two digits also, like 9 plus 2 is 11. You can still add those two digits also, but while searching also you should perform the same procedure. If the index is valid, you can store the element there. Otherwise, you can again add those digits and you can fold those digits and you can generate a new number that is mapping inside the hash table or within the range of size of the hash table. So this is about numeric keys. Now, if suppose a key is a string, I have a string as a key, ABC. Suppose this is a key ABC. It can be a name of a person, name of a product, or anything it can be. So I am just taking alphabets ABC. Now how this can be converted into a index in a hash table? So for this we can take ASCII codes of these alphabets like A, B, C, 65, 66, 67. This is forming three different numbers, so you can make it as a single number. Now this is like a single number, and this we can perform folding by taking 65 plus 66 plus 67. We can add all these. 8 carry 1, 198. Now this is forming three digits. Suppose this is going out of range, again perform mod, or else you can skip this carry if you want just two digits. That's up to you. So this is how a string can be converted into an index with the help of their ASCII codes. Now finally, conclusion is you can design your own hash function. Whatever the hash function you like, you can design it. Make sure that always it gives the same result. Means whenever you are passing a key 1, 2, 3, 3, 4, 7, then always you should get 11. Suppose if you are getting 11, you should always get 11. It's not that one time it has given some number, some other time it is giving some other number. That is not a suitable hash function. So hash function should always give you the same index. Now while storing, it has given the index, we will store it. While retrieving, again it gives the index, we go there and find it. That's all. So designing hash function is up to a designer or a programmer. So he can choose anything he wants. Even a programmer can have his own idea and he can introduce his own hash function. These are just the ideas. So depending on the data, you can think over it and you should design some hash function which avoids collision. Then one more thing, that languages like Java and .NET, these languages provides built-in hashing. Like in Java, whenever you create an object, a hash code is given for that object. That hash code is automatically generated by JVM on a system. So it may be using date and time and the location and various other values as a parameter and generating some hash code, so that that code will uniquely identify a object created. So universally it will be unique and it will be uniquely identified. So hash codes are more important in Java. You can identify any object with its hash code. So those hash codes are generated by using some parameters. So even we can design our own system where we can generate the hash code for every value that we want to store in hash table, and we can have our own hash function which is uniformly distributing the values. But in these examples we have been using the key that is a part of data. It is not a generated key. The key is a part of a data. Suppose this is a key or this is a key, or else we can have our own keys for the objects. So that's all about hashing technique. So we have discussed various topics under hashing technique. So you practice these programs, this will develop your programming skills and analytical skills.